So today let us discuss Stokes theorem. So actually Stokes theorem is analogous to, so always we try to find analogy to electrical field. That is just to make your mind refresh about what we have studied in electric field and how electric field and magnetic field can be related, so that you don't have confusion regarding the terminologies. That's okay. So Stokes theorem is analogous to divergence theorem in electrostatics. We have studied what is divergence theorem in electrostatics, right? So you can change a volume integral, okay, over a volume to a surface integral, right, over a closed path or a closed surface, is it not? So that is divergence theorem, right? So we have studied it for flux density. So volume integral del dot d dv is surface integral d dot ds. That is divergence theorem. So this Stokes theorem is something very analogous to it. Okay, very analogous to it. So here Stokes theorem relates line integral and surface integral. There it was volume integral and surface integral. Here it will be line integral and surface integral. Okay, so Stokes theorem basically relates line integral to surface integral. Okay, so it's a mathematical theorem which we apply this to magnetostatic. Okay, mathematical theorem means which it is necessary to know the statement of the theorem and a mathematical expression to apply to the magnetostatics. So the statement of Stokes theorem is the line integral of any vector. Line integral of any vector around a closed path, okay, is equal to integral of curl of that vector over an open surface enclosed by the path. Okay, so line integral, repeat, line integral of a vector, any vector around a closed path is same as integral of curl of that vector over an open surface enclosed by closed path. Okay, enclosed by closed path. We'll write the statement later. Okay, it's not that we'll write the statement and prove it, because basically there is no proof for this. I'm just trying to obtain the expression for Stokes theorem. So this is a statement for Stokes theorem. So it is my duty to obtain mathematical expression for this statement. Okay. Now you might have noticed that I used the term open surface. Usually we say closed surface. That's it, right? Closed surface. We usually use the terminology closed surface. Now I am specific here. I am talking about open surface. So Stokes theorem, this is very important. Okay, if you make mistakes here, Stokes theorem can be applied only to open surface. Okay, what is the difference? When I say closed surface, okay, it involves volume. What is a closed surface? A surface which is closed. Okay, a football. A football has a volume inside, right? A cricket ball, a football, right? So it's a closed surface. You know that. Gaussian surface, right? We have taken such closed surface as Gaussian surface. So it involves volume. So the moment surface comes, it involves volume under it, within it. Stokes theorem cannot be applied in such cases. Stokes theorem cannot be applied to volume at all. Surface, that is very imaginative now, right? Open surface is a surface like this, which is not closed. There is no volume enclosed under this surface. Okay, it is free area under this surface. Is that okay? You hold a paper in your hand. Okay, hold a paper in your hand. That is a surface. Okay, but it's an open surface because it is not closing anything. Okay, so you remember this. Okay, Stokes theorem can be applied only for open surface. Okay, now look at the figure what you have on your whiteboard. Okay, well, look at the figure which you have on the whiteboard. I'm going to consider a surface whose area is capital S. Consider a surface whose area is, okay, capital S. And this capital S is splitted into number of small incremental surfaces. Okay, small incremental surfaces. Then each incremental surface area is delta S. Each incremental surface area is delta S. Okay, so I have considered an uneven surface. Okay, I'm showing this as an uneven surface to make sure that the style or the shape of the surface doesn't matter in our explanation. That's the only purpose. Okay, so I have divided into so many smaller surfaces, incremental surfaces, and if I want to consider this delta S as a vector, then you know that I always consider the direction to be normal to it. So that's why that A n cap is indicative. Okay. Now applying the idea of curl of H. So we have already studied curl of H, right? So applying the idea of curl of H. So curl of H in normal direction. Okay, curl of H in normal direction is what? Closed integral H dot dl of, okay, H dot in general, H dot dl divided by area, right? This is what we get, curl of H. Okay, in general. So here we have dl for a small surface area delta S. So this can be written as closed integral H dot dl vector for delta S divided by delta S. Okay, so here dl delta S will be perimeter of incremental surface delta S. That you have to remember. Okay, it's the perimeter length. dl vector is the perimeter length of incremental surface area. Okay, delta S. If I integrate it, I'll get the total surface area. Length of the capital S. Okay. Curl of H normal as curl of H dot n cap. Is it not? Because this is just a representation, so I'm mathematically writing it as curl of H dot n cap. I can write it as curl of H n cap. Okay. Now substitute this this in this expression. You write curl of H n curl of H n cap. Then what we get? Okay, just equate that equation. So curl of H normal is written mathematically as curl of H n cap, which is equal to closed integral H dot dl delta S divided by delta S. So I take this delta S to LHS, so I get curl of H an cap dot n cap delta S is equaling closed integral H dot dl delta S. Now see here, delta S an cap, delta S an cap. See the figure, delta S an cap can be written as delta S vector because it is magnitude of delta S into direction of delta S. So it can be written as delta S vector. So this becomes curl of H dot delta S vector is equaling closed integral H dot dl delta S. Okay, yeah. Now listen carefully. Now listen carefully. Okay, or for further explanation, okay, you may require one more figure. Okay, so let us go to that figure first. That is this figure. Okay, so I have just redrawn the incremental surfaces which we have in the initial figure. Okay, now with reference to that equation which we got just now, if you want to get the total curl, right? Total curl. So that is curl of H dot delta S. Curl of H dot delta S. Now if I want to get the total curl, then you have to add all the closed line integrals for each delta S. Is it not? So it is basically integration of that. I agree. But it is same as when it is not a differential surface, it is delta surface. Okay, summation will do. Is it not? So it is basically adding all these incremental surfaces to get the final S. Final S. Okay. Now see, if you travel through this each incremental surface, okay, it's interesting. Listen carefully. If you travel through each, for example, this, okay. So when you are taking the current direction anti-clockwise, so when I'm traveling like this, I come like this, okay, I go like this, I come like this, I go like this. Next, when I take the down segment, I go like this, again I come like this. See, this and this cancels. Then I come like this, go like this. For this will go like this. Okay, so this is true for each segment. For each delta S, okay, sharing common boundary between another delta S. Okay, so the evaluation of curl will cancel each other. Getting what I'm trying to say? They cancel each other because this is in this direction. Okay, for the other, the current direction is like this. So this and this cancels. In this, like this, cancels. In this side, it is like this, cancels. This side is opposite to each other, cancels. So this is true for every delta S. Means this is true for every interior boundary. But what about this exterior boundary? There is nobody to cancel here, right? So you have current flowing like this. Okay, you have current flowing like this. You have current flowing like this. Okay, like this, like this, like this. So it continues like this. Getting, so there is no cancellation on the outer surface. I hope it is very clear. There is no cancellation on the outer surface. So only the outer surface remains now. All the incremental surfaces, that is inside surfaces, gets cancelled. Get cancelled. So what does it mean? So instead of writing, okay, instead of writing closed integral h dot dl delta s, I can write it for the total s. I can write because there is only one surface now. I understood that all incremental surfaces, when I trace, okay, when you calculate the curl for individual delta s, they cancel each other. So there is no meaning in writing now dl delta s because the perimeter of internal surfaces are not important for me now. I just want to calculate the perimeter of the outer surface. That is the main surface. That is the total surface. So this can be written as closed integral h dot dl total surface. So this is basically better written as closed surface integral h dot dl. Clear? Better way of writing. So my LHS is now closed surface integral h dot dl. Okay. Now what is RHS? RHS was curl of h dot delta s, right? Curl of h dot delta s vector. Okay, that was the equation. Okay, leave it RHS or LHS. Okay, curl of h dot delta s is equal to integral h dot dl delta s. So h dot dl delta s now becomes a surface integral h dot dl, and curl of h dot delta s, the delta s will become now differential surface ds, because when we are integrating, actually the delta s is now single s, but I have to integrate it over the total surface because surface area is not known to me, so I have to integrate it over the total surface. So the other side of the equation becomes, okay, surface integral curl of h dot ds. Okay, now I did a small mistake here. Listen, this d, see, I am integrating this h with respect to dl. Dl is the perimeter of area, right? Means perimeter of the path. Okay, perimeter of s. So perimeter of s is line integral. Okay, not surface integral. So this is L. Okay, line integral. So line integral h dot dl. This is line integral because I am integrating with respect to dl. Dl is length. Okay, so this is length integral. So closed integral line h dot dl is surface integral curl of h dot ds. This is Stokes theorem. This is Stokes theorem. Is it okay? So if you want, I'll write it neatly once again, the equation, okay, to avoid any confusions. So Stokes theorem says that line integral h dot dl is equal to surface integral curl of h dot s. Okay, so this was the statement. Okay, this was the statement of Stokes theorem. That is the line integral of a vector. So here vector is h vector. Okay, so the line integral of h vector around a closed path is equal to integral of curl of that vector over the open surface. See here, this is closed line integral. This is just integral s. So it indicates that it is open surface integral. Okay, so surface, open surface enclosed by the path. Okay, because that perimeter of the path is outer surface. So whatever you have inside that, only that you have to calculate. So that is Stokes theorem.